Hello, class. This is Mr. Hart, and in this podcast, I want to finish up the pressure and fluids unit, and we want to cover fluid flow. So everything up to this point has been just kind of static fluid or fluid that's not moving. In this case, we want to look at what happens when fluid is actually flowing. Okay, but before we do that, we want to think about how fluid flows. Okay, and sometimes we like to think of fluid as this nice, smooth flow with little resistance, doesn't have any problems as it goes through tubes and things like that. But oftentimes, when fluid does flow, what we get is what we call turbulent flow or turbulence. Okay, if you think about water going down the drain or down a pipe or something like that, usually it's not nice and smooth like this. There's a little bit of turbulence, a little bit of resistance. Okay, think about air flowing. When wind blows, there's definitely lots of turbulence and stuff like that. Okay, so we kind of have this ideal situation, which we call streamline or laminar flow. Okay, but this doesn't happen very often. This is a very unique case. Most of the time, we have what we call a turbulent flow. Okay, a lot of resistance, a lot of going back and forth, things like that. Okay, but when we do the math and physics for fluid flow, we usually like to think of the streamline flow just because it makes the math a little bit easier. Okay, we're making an assumption, but it helps us kind of get some better results, something that we can use. Okay, and so we have what we call an ideal fluid, or basically a fluid that receives no resistance as it passes through a container. Okay, and again, this isn't a realistic situation. Most fluids are not ideal, but we're going to make this assumption when we do the math just to make the math a little bit easier. Okay, and we'll still get pretty good results from this. But again, we are thinking things as an ideal fluid. Okay. Then another vocabulary word we want to think about is fluid flow rate, or basically the amount of fluid flowing through a container in a given amount of time. Okay, and the key word here is the amount of fluid. So think about like if you've ever put your thumb over your garden hose and the water shot out faster. Okay, in that case, the fluid isn't actually flowing any faster because the same amount of water is coming out at the same amount of time. So it may appear to be moving faster, which is true, but the fluid flow rate is staying the same, right? The amount of fluid coming out is the same. Okay, so we don't want to get this confused with the speed of the fluid. Um, the fluid flow rate is actually the amount of fluid coming out at a certain amount of time. Okay, so just make sure you're clear on that. Don't get confused with the fluid speed. Okay, the fluid flow rate, it has to do with the amount. Okay. All right. So let's think more about this fluid flow. Okay. So let's say I have a container and it starts with a large pipe and water's flowing through this or some type of fluid, and then it quickly shrinks down to the smaller pipe. Okay. Kind of like when you put your thumb over your garden hose. Okay. It's going from a large wide opening container to a very small opening container. Okay. And in this case, the fluid flow rate, here's the key idea, the fluid flow rate at any point in the container is constant. Or, in other words, the same amount of fluid will get through in the same amount of time. Okay. And so, like, for example, if we think about this fluid right here in this container, okay, it may be flowing at a certain velocity, which we'll call V1. And it may be pretty slow. It'll be flowing through this container very slowly, okay? But it also has a very large opening, which you call area 1. Okay, so there's going to be a lot of fluid flowing through here, okay? And then it shrinks down, and now we go to this smaller container, and now it's going to be a much higher velocity, right? V2. So more fluid is going to be passing through at a quicker rate, but now the area is a lot smaller, okay? And so if we look at any point in the container, the fluid flow rate is the same. It's going to be some constant. Okay, it doesn't matter if we're shrinking size or increasing size, the velocities are going to compensate so that the same amount of fluid gets through in the same amount of time. Okay, and so when we do that all out, we get what we call the fluid flow equation, or basically this conservation of fluid flow rate. Okay, and it says the area of the first container, A1, times the velocity in the first container, V1, is equal to the area in the second container, A2, times the velocity in the second container, V2. Okay? Or if we look at this picture, okay, the area 1 times the velocity 1, that's the fluid flow rate in that container, has to be the same as area 2 times velocity 2, or the fluid flow rate in that container. Okay, so this is a really powerful equation. It helps us be able to solve for fluid flow, okay, as it passes between different, containers, different sizes, okay. But again, it all comes from that key idea that no matter what the container size is, the same amount of fluid is going to get through in the same amount of time. Okay, so let's try this equation out. So you have a garden hose that has a cross-sectional area of 5.3 centimeters squared, and the water is coming out at 1.8 meters per second. If you put your thumb over the nozzle, the area decreases to 2.1 centimeters squared. What will be the velocity of the water when your thumb covers the hose? Okay, so again, common scenario, we know the water is going to shoot out faster, but we want to actually calculate that speed. Okay, so we know that before we put our thumb over the hose, the area of that hose, or the cross-sectional area, is going to be 5.3 centimeters squared. Okay. And we know that when it's just flowing at its own speed, okay, its velocity is 1.8 meters per second. Okay. And so then we put our thumb over the nozzle, and we know that the area decreases to about 2.1 centimeters squared. So A2 is going to be 2.1 centimeters squared. Okay. And that's the information we know. So we're looking for that new velocity. What's the velocity of that water as it comes out? Okay. We know it's going to be faster because it's trying to get the same amount of water through in the same time. Let's actually figure it out. So we get A1 times V1 equals A2 times V2. Okay. Again, these V's are velocities, not volumes. Okay. But now we're solving for V2, the velocity in the second container. And so we need to get it by itself. So we're going to divide this A2 and bring it over here. Okay, so we're going to divide by A2 and bring it over here. And so now we have A1 times V1 over A2 gives us V2. And so now we just got to plug in the numbers. So we get V2 equals A1, which is 5.3, okay, times V1, which is 1.8, over A2, which is 21 centimeters squared. Okay, and so there we go. Or sorry, not 21, 2.1. 2.1. All right, so last step, we just plug that in our calculator, and I'm going to pull that out really quick. And so we get 5.3 times 1.8 divided by 2.1, and we get 4.54 meters per second. Okay, there you go. So there's your answer. That the faster moving water is going to be moving at 4.54 meters per second. Okay, so again, we can actually calculate how fast that water has to be moving in order to conserve the fluid flow rate. Okay, so pretty cool. All right, and so again, you're just manipulating this A1 times V1 equals A2 times V2 equation. Okay, so if you're doing this for participation, answer this question. Okay, a river with a width of 5 meters and a depth of 3 meters forces water into a small opening. The water moves through the river with a velocity of 0.5 meters per second. The water going through the opening is moving at 1.5 meters per second. How big is the opening? Okay, so in this situation, it's kind of reversed. You're going to be solving for A2 instead of V2. Okay, but I'll give you a quick hint really quick. This 5 meters and this 3 meters are the width and the depth. This is not an area, so you got to think about how you would calculate the area of that square. Okay, and so if you think it through, the width times the depth is the area. So your A1 is actually going to be 15 meters, 5 times 3. Okay, so there's your big hint. That's the first quantity you're looking for, and then find the other ones and calculate the new area. Okay. Again, if you're doing this for participation, go ahead and give that a try. All right, but let's move on. Okay. You were assigned homework 10 in class, so if you haven't done that yet, make sure you get that done. And then the last thing we want to talk about is what we call Bernoulli's principle. Okay, this is a key idea of fluid flow. And basically it says this: the pressure of fluid drops as the velocity increases. Okay, so the faster the air is moving, or the fluid, or the water, whatever it is moving through a container, the lower the pressure it gives. Okay, I like to think about this in terms of like freeway traffic. Okay, if you've ever driven on the freeway, okay, and you've seen how far the cars are spread apart, okay, because they're moving so fast, okay, they have to be pretty spread apart. You're never going to tailgate someone on the freeway, or at least you shouldn't. It's a terrible idea, because if you do, if you do and they need to stop or slow down quickly, you're going to crash, right? So cars like to spread out quite a bit when they're on the freeway, okay? Whereas if you're on just a local road, you could have lots of cars pretty close together, okay, because they're not moving too fast. Okay, they can be closer together because they're going at a lower speed. But on the freeway, at a higher speed, they have to be pretty far apart because they don't want to hit into each other. Okay, air particles are the same way, or fluid particles are the same way. The faster they're moving, the farther out they want to be spread apart, and so their pressure they're going to exert is lower. Okay, they're going to exert a lower pressure. Okay, so this is what Bernoulli discovered, is that this faster moving fluid, faster moving air, faster moving water is going to be giving a lower pressure. So let's look at an example of that. And a very practical example is airplanes, okay, and airplane wings, okay. So if you think about an airplane, you want it to get up off the ground, right, which means you want some type of force pushing upwards on the wing, right? In order to do that, if you're only using air as your force, then you're going to want a higher pressure up here and a lower pressure right here, right? So it's going to push the air, or the higher pressure is going to push towards the lower pressure, which is going to give this upward force, which is going to lift up the airplane. Okay, so in order to do that, they want to make the air on top move faster because that will make it at a lower pressure, according to Bernoulli's principle. So if you've ever seen an airplane wing, you'll notice that the bottom's very flat. Okay, the bottom's very flat along the airplane wing, and the top is very curved. Okay, the reason for that is if the airplane wing is curved at the top, this air at the top has to travel farther to get to the same point. So it's actually moving faster. So this air right here, okay, is moving faster than this air down here. Okay, and so it's moving faster because it has to go farther in the same amount of time because of this curved wing. Okay, and since it's moving faster, this gives it a lower pressure. Okay, so Bernoulli's principle makes that lower pressure, which causes the airplane to lift. So that's a very practical use of Bernoulli's principle right there. Okay, in the design of airplane wings. Okay, I also did in class a demonstration with a leaf blower and a little bouncy ball, and you can actually keep the bouncy ball within the path of the leaf blower because as the leaf blower is blowing, okay, this is our leaf blower, and it's shooting air out the top, okay, and you have like a bouncy ball or a tennis ball, something in that airstream, okay, because all this fast moving air is coming out of the leaf blower, okay, the air in the center, I'll do this in a different color, the air in the center is actually going to be at a lower pressure, okay, and you're going to have a higher pressure on the outside. And so because of that, you're going to get a force pushing in towards this lower pressure, which is able to keep the tennis ball in its spot. Okay, so that's a really cool demo. Again, using Bernoulli's principle, lower pressures mean, or faster moving air means lower pressures, which gives us a nice force on objects. Okay. I also did a demonstration called the Bernoulli bag. Okay, which is a example where I can fill this giant bag full of air. Okay, not by blowing in my own air into the bag, but causing a lower pressure in the bag. So if I blow fast air right here, it causes a lower pressure, and you have the high pressure out here, okay, on the outside. So I can just do a little quick blow, not too much air, and all the outside air is going to come in from that high pressure because it's trying to get towards this low pressure. So that's another cool demonstration. Rather than trying to fill the bag with my air, which takes forever, I just blow fast air in front of it, and the air from the outside will actually fill it in for me. Okay, so that's a pretty cool demonstration as well. Okay, then the last one we'll go through today is what I call the train example. Okay, so this is a really interesting scenario. So imagine you have a train track. Oh, I'm sorry for my bad drawing. I'm using a touchpad, so forgive me for the non-straight lines. But you have a train track, okay, and you have a train going down the track, okay. Let's say it's right here. Here's our train, and it's moving down the track at a quick speed. A lot of people think if I was standing like right here, a lot of people think that the train will, shoot this gust of air and throw me back in this direction because of the large, blast of air that is moving in front of the train. Okay. But that's actually not the case. That's kind of a misconception that we get from, movies and Hollywood. Okay. If I'm actually standing right here, that's not too good because if you think about it, this train's moving really fast, which means it's causing a low pressure in front of it and behind it because of these fast moving air or because of this fast moving air. And so now you have a high pressure on the outside. Okay. And so instead of blowing me toward or away from the train, it actually blow me towards the train. This air would push me towards the train and kind of suck me in. Okay. So you don't want to be standing too close in front of a train or to the side of a train because it's not going to push you back. It's actually going to push you in, which is a lot more dangerous. Okay. But again, that's just Bernoulli's principle. And so that's a really interesting example of what you don't want to do because of Bernoulli's principle. Okay. But hopefully that makes sense. I know we covered a lot with fluid flow, but it's a really interesting concept. Okay. So make sure you understand the fluid flow equation. Okay. The A1 times V1 equals A2 times V2. And also Bernoulli's principle that faster moving air has a lower pressure. Okay. But hopefully that all makes sense. Please let me know if you have any questions, and thank you for watching.